Hi everybody. In this video I'm going to briefly introduce some of the fundamentals of X-ray diffraction, which I hope will be helpful to you in the lab that we're doing. First, just a few quick notes about the importance of X-ray diffraction. XRD really has become the dominant approach to solve all types of crystal structures, whether it's ionic or molecular or biological. And the way that X-ray diffraction works is that it allows us to deduce the structure based on the interference pattern that results when X-rays scatter off electrons. So you shine an X-ray beam at a sample and you see bright spots and dark spots in certain places, and that allows you to figure out where the atoms are. X-ray diffraction was developed in the 1910s, and it really is used in much the same way today, although the process has become more automated. These three scientists, Max von Laue and William and Lawrence Bragg, who were father and son, were among the early developers of X-ray diffraction, and they won Nobel Prizes in physics in 1914 and 1915. Since the scientists in these pictures are not a particularly diverse-looking group, I do want to make a brief historical note. X-ray diffraction, more than a lot of other fields, has a long history of great and historically significant female crystallographers. And if you look at the stories of some of those scientists, you see some pretty glaring examples of gender bias. One example is Rosalind Franklin, whose work was crucial to the solving of the crystal structure of DNA. You may be more familiar with the names of Watson and Crick, who are more recognized for having solved the structure of DNA. Rosalind Franklin's unpublished work was basically used without permission by Watson and Crick, and as a result, her contribution isn't as widely recognized. Another crystallographer who did receive some more recognition was Dorothy Hodgkin, who solved the structures of some large biological molecules and won the Nobel Prize in Chemistry in 1964. So on the surface, it seems like Dorothy Hodgkin received more recognition. And yet, if you look at some of the British newspaper headlines from when she won the Nobel Prize, you see some absolutely ridiculous things like Nobel Prize for British wife and Nobel Prize for wife from Oxford. So I'll leave it at that, and we'll move on to the science. Before we can talk about how X-ray diffraction works, we need to talk a little bit about crystal structures in general. A crystal is a chemical structure that has translational symmetry, which means that it's basically a box of atoms called a unit cell that repeats itself over and over again in space, left to right, front to back, bottom to top. The unit cell can be a cube, but it doesn't have to be a cube. The lengths of the edges can be different, and the angles don't have to be right angles. The unit cell can be a small box of a few atoms, like in sodium chloride. It can be a larger molecule, like in sucrose, or it can be a really large biological molecule, like the protein shown on the right. All of these are crystals, and all of them are the types of structures that can be solved by X-ray diffraction. More formally, a unit cell can be defined by three basis vectors, A, B, and C, that define the edges of the unit cell. When we say that a crystal has translational symmetry, we mean that we can move any integer number of basis vectors, an integer times A plus an integer times B plus an integer times C, and end up in an equivalent place in the unit cell. The crystal looks exactly the same when we move an integer number times the basis vectors. I'd also like to say a few things about symmetry in crystal structures. A crystalline unit cell can have one of 14 different symmetries, and those symmetries are called Bravais lattices. The Bravais lattices that we'll be thinking most about in this lab are the three cubic Bravais lattices, the three lattices where the unit cell is a cube. One of those is the primitive cubic Bravais lattice, where there's a lattice point at each vertex of the unit cell. Another is the body-centered cubic Bravais lattice, where there are lattice points not only at each vertex, but also at the center of the unit cell. And the third is the face-centered cubic Bravais lattice, where there are lattice points at the vertices and also at the center of each face. These are the three different symmetries that a cubic unit cell can have. I should emphasize the difference between a Bravais lattice and a crystal structure. Each red circle in these pictures doesn't necessarily represent an atom. It represents a lattice point. That means that whatever exists at the red circle, whether it's an atom or a molecule or some other motif of atoms, has to exist at every red circle. If a crystal has, for example, a body-centered cubic Bravais lattice, it's possible that it's a body-centered cubic structure. It's possible that each of those red circles does represent an atom. But it's also possible that at each one of those red circles, there's some more complicated geometry of atoms, and that the same thing exists at each circle. So 3 of the Bravais lattices are cubic, and the other 11 are lower symmetries. In what are called tetragonal and orthorhombic Bravais lattices, the edge lengths of the unit cell can be different. And then in hexagonal and monoclinic and triclinic Bravais lattices, the angles between the unit cell vectors don't have to be right angles. In this lab, we won't really worry about the non-cubic Bravais lattices, but it's good to be aware of them. In thinking about Bravais lattices, we've only been thinking about the translational symmetry of the unit cell. We haven't even considered the symmetry of the atoms within the unit cell. In inorganic chemistry, you learn that molecules can have all sorts of different point symmetry operations, like mirror planes and axes of rotation, and that those molecules can have different point groups. Crystals also have point symmetry operations. And when you combine the point group symmetry with the translational symmetry, crystals can actually have one of 230 space groups. Space groups are just the crystal analog of what point groups are to molecules. So as you can see, symmetry in crystals gets pretty complicated, but in this lab we won't really worry about it beyond the 3 cubic Bravais lattices. Now we can get back to actually talking about X-ray diffraction. The first thing you might be wondering is, why is it X-rays that we use to determine structure? Why not infrared light or ultraviolet light or something else? From a big picture standpoint, the reason we use X-rays is that the wavelengths of X-rays are on the angstrom scale, which is similar to the spacing between atoms in a crystal. So it's X-rays that give us an interesting diffraction pattern when we shine a beam at a crystal. So when you do an X-ray diffraction experiment, you shine a beam of X-rays at a crystal, the X-rays scatter off the electrons in the crystal, and produce an interference pattern where you see constructive interference or peaks at specific angles. Based on the positions and the intensities of the peaks, it's possible to determine where the electron density was. And if you know where the electrons are, you know where the atoms are. These are examples of what the results of an X-ray diffraction experiment look like. On the left is a single crystal X-ray diffraction pattern. That's what you get when you have one big continuous crystal that's oriented in a particular direction. As you can see, you get bright spots in particular places in 2 dimensions on a detector. On the right is a powder X-ray diffraction pattern. That's what you get when you have not a big single crystal, but a lot of small crystallites that are oriented randomly in different directions. As you can see, in a powder X-ray diffraction pattern, you actually get less information. You get peaks in terms of just a single angle that we usually call 2 theta, because your information is averaged for all of the different orientations of crystallites. Both of these methods are widely used. Single crystal X-ray diffraction is more informative, but often all you have is a powder if it's not possible to grow a single crystal. For most of the rest of these slides, I'll be talking about issues that are relevant to powder X-ray diffraction. So, at what angles do we expect to see constructive interference? At what angles do we expect to see bright spots in an X-ray diffraction pattern? To figure that out, we need to understand what's called Bragg's law. The easiest way to arrive at Bragg's law is to simplify our view of what a crystal is, and think about it as a series of planes of atoms that are separated by a distance d. This is obviously a big simplification, since a crystal is a whole 3-dimensional array of atoms and not just parallel planes. But let's go with it. Now imagine that a coherent X-ray beam comes into the crystal at an angle theta. When I say a coherent X-ray beam, I mean all the peaks and troughs of the X-ray beam are lined up. When the X-ray beam arrives at electrons in the crystal, it has some probability of scattering off each plane of atoms. Eventually, the X-ray beam leaves the sample. This picture is showing us 2 possible paths that the X-ray beam can take through the crystal. One where it scatters off the top plane of atoms, and one where it goes 1 layer deeper and then scatters off the second layer. In each of these paths, the X-ray beam travels a different distance. If the planes of atoms are separated by distance d, and the angle of the X-ray beam was theta, then we can do a little trig to figure out that the path difference between those 2 paths is 2d sine theta. We know that the X-ray beam came into the crystal with all of its peaks lined up. And what we want to know is whether the X-ray beam also leaves the sample with all of its peaks lined up. That's what would result in constructive interference. That's what would result in a bright spot in our X-ray diffraction pattern. In order for that to happen, the path difference between those 2 paths has to be an integer number of X-ray wavelengths. So the path difference is 2d sine theta, and if that's going to be equal to an integer number of wavelengths, that's some integer n times the wavelength of the X-ray beam, lambda. This is Bragg's law in the bottom right corner of the slide. 2d sine theta equals n lambda. Still, there's something kind of strange about this. Bragg's law is given in terms of a distance d, the distance between atomic planes in the crystal. And we're not exactly sure which planes we're talking about. You could imagine a lot of different sets of atomic planes within a crystal, so we need to think a little bit harder about what planes we're even talking about. The sets of atomic planes that we're concerned with in X-ray diffraction are what are called Miller planes. Each diffraction peak corresponds to a set of Miller planes, which are specified by three integers h, k, and l, which are called the Miller indices. The definitions of h, k, and l are given in these equations. They're the reciprocal of the spacing between planes in the a, b, and c directions. This definition is kind of confusing, and I think it's easier to understand in pictures. So I'm going to show pictures of Miller planes in a two-dimensional crystal. In 2 dimensions, there are only 2 Miller indices, but we'll be able to imagine how this will work out in 3 dimensions. Here's a picture of a set of Miller planes in a 2-dimensional square unit cell defined by vectors a and b. To figure out the Miller indices of this set of planes, we need to think about the spacing between the planes. In the a direction, these planes are spaced by half the unit cell edge length. The reciprocal of 1/2 is 2, so the first Miller index is 2. In the b direction, the planes are spaced by 1 unit cell. The reciprocal of 1 is 1, so the second Miller index is 1. So this set of Miller planes in a 2-dimensional crystal would be called the 2-1 planes, and it's written like this. We don't say the 21 planes, we say the 2-1 planes. Here's another example of a set of Miller planes, again in our 2-dimensional square unit cell. The spacing in the a direction is 1 unit cell, the reciprocal of 1 is 1. And you can think of the planes as being infinitely spaced in the b direction. If you go from one plane and move in the b direction, you never run into another plane. The reciprocal of infinity is 0, so the second Miller index is 0. These are the 1-0 planes. As you can imagine, Miller planes in a 3-dimensional crystal would have 3 Miller indices because you can look at the spacing in the a, b, and c directions. In principle, you can see X-ray diffraction peaks corresponding to any set of Miller planes with integer Miller indices. But the question of whether a given diffraction peak is strong, whether it has high intensity, is another question entirely. An X-ray diffraction peak is strong if and only if the atoms actually lie near the Miller planes, and not sort of halfway between them. So now let's again think of the sets of Miller planes in our 2-dimensional crystal, but now also consider the positions of the atoms. These are sets of Miller planes for a square unit cell where the atoms lie at the vertices of the unit cell. You can see that for each of these sets of planes, all of the atoms lie exactly on the planes. As a result, we expect the diffraction peaks corresponding to each of these sets of Miller planes to be strong. In fact, in this crystal we expect all peaks corresponding to integer Miller indices to be strong. But that may change when you put more atoms in the unit cell. If equal numbers of atoms lie on the planes and between the planes, a diffraction peak could be missing entirely, which is called a systematic absence. Now we're looking at the same sets of Miller planes, but for a square crystal where atoms lie at both the vertices of the unit cell and in the center. You can see that for some sets of planes, like the 2-0 planes and the 1-1 planes, it's still true that all of the atoms lie on the planes. This means that the 2-0 peak and the 1-1 peak will be strong for this crystal. In contrast, for the 1-0 planes and the 2-1 planes, the atoms at the vertices lie on the planes, but the atom at the center of the unit cell does not. It lies halfway between the planes, and it actually completely cancels out the interference of the atoms at the vertices. So the 1-0 peak and the 2-1 peak are entirely absent for this crystal. This is an example of a systematic absence. As we're about to see, something very similar happens in 3 dimensions. When we have a crystal with a face-centered or a body-centered cubic Bravais lattice, certain peaks are absent. By looking at which peaks are absent, we can figure out what type of Bravais lattice a crystal has. We won't derive them in this video, but here are the rules for which peaks are present for different types of cubic Bravais lattices. For a crystal with a primitive cubic Bravais lattice, all peaks corresponding to integer values of h, k, and L are present. For a crystal with a body-centered cubic Bravais lattice, the peaks that are present are the ones where the sum of h, k, and L is even. And for a crystal with a face-centered cubic Bravais lattice, the peaks that are present are the ones where h, k, and L are either all even or all odd. That means we can figure out the Bravais lattice of a crystal just based on whether peaks are present or absent. If we want to completely solve the crystal structure, to figure out where the atoms are, we need more information. We need to think about the relative intensities of the peaks, and we probably need a computer to solve the structure. This goes beyond what we're going to cover in this video. Once we've determined the Bravais lattice and the Miller indices of each of the peaks, we can then figure out the size of the unit cell, the length of the cell edge. Again, we're going to focus just on cubic crystals in this video. If we call the edge length of a cubic unit cell A0, and look at a set of Miller planes with indices h, k, L, we can use some trig to find that the distance d between the planes is A0 over the square root of h squared plus k squared plus L squared. We can then take that expression for d and substitute it back into Bragg's law, which we saw earlier in the video. We'll assume that n, the number of wavelengths in the path difference in the X-ray beam, is 1, because the wavelengths of X-rays are pretty similar to the spacing between atomic planes in the crystal. So we now have an equation that looks like this. And because we've already figured out the Miller indices of each peak, h, k, and L, and we know the wavelength of the X-ray beam, lambda, that means that this equation allows us to relate the peak positions, the values of theta for each peak, to A0, the edge length of the unit cell. So in principle, it's possible to find A0 just from the position of one peak, but we can do a better job if we use all of our data and average the values of A0 that we get based on the positions of each of the peaks. Finally, the last thing I'd like to talk about is the average crystalline domain size in our sample. If we had an infinitely large perfect crystal, then the peaks in an X-ray diffraction pattern would be infinitely sharp. But in reality, a powder sample has small crystallites that are oriented in different directions. And if a crystallite is small, then Bragg's law doesn't have to be followed as perfectly, and the peaks in the spectrum are broader. Based on the width of our peaks, we can actually estimate the average crystalline domain size in our sample. The broader the peak, the smaller our domains are. And when I say domain, I'm talking about a region where the crystal structure is continuous. The equation that relates the broadness of the peaks to the crystalline domain size is this one, the Scherer equation, and I'll walk you through what these different symbols stand for. Tau is the average distance across a crystalline domain, it's a length. Capital K is a unitless shape factor. It's basically a measure of how spherical the domains are. We usually take the value to be 0.9. Lambda is the wavelength of our X-ray beam. If it's copper K alpha 1 radiation, which it usually is, it's 1.5406 angstroms. And beta is the broadness of the peak, usually taken to be the full width half maximum of the value of 2 theta in radians. So in this equation, tau has units of distance, lambda has units of distance, and everything else is unitless. That brings us to the end of the video, and I'd just like to recap some of the things that we've talked about. We started by talking about crystal structures and Bravais lattices. We then talked about Bragg's law to show why we see interference patterns with X-rays. We talked about the sets of planes within a crystal, Miller planes and their Miller indices. And then we showed how we can use a powder X-ray diffraction pattern to find a few important things about crystals. The Bravais lattice based on which peaks are absent, the edge length of the unit cell based on the angles of the peaks, and the average crystalline domain size based on the widths of the peaks. Thanks for watching.